let's look at composite functions. We have two functions here, f, which is a straight line, 2x plus 1, and we have g, which is a quadratic, x squared plus 3. Now the thing to take note here is that f has a restricted domain between -1 and 2, and g doesn't have any restrictions on the domain. So we're asked to find g of f of 1, an equation for g of f of x, and the domain and range for g of f of x. So this notation here is what we call a composite function. We have a function f that's stuck inside a function g. You might sometimes see this notation, so this notation here, written with a circle instead, g little circle f. So that's the function g of f, and when you want to substitute things in, you put brackets around as so. Okay, let's see how this works. So let's work out what happens if we substitute 1 into the composite function g of f. So to do so, we need to work out the inside bit first. So I'm going to work out f of 1 just to make the problem easier. So we're going to substitute 1 in for x into 2x plus 1. So 2 times 1 is 2 plus 1 is 3. So this bit here equals 3. To finish working out the problem, we now need to work out g of 3. So what that means is we sub 3 in for x into g's equation, x squared plus 3. So 3 squared plus 3, which comes out to be 12. So all in all, the answer to part A, using function notation, g of f of 1 has 12 as its overall value. Okay, let's do the same thing now for B, but instead of substituting in x equals 1, we're going to leave x as it is. So we're going to do the same thing. We'll sub in x into f of x. So we have f of x equals 2x plus 1. And now we need to substitute 2x plus 1 in here. So we'll substitute in g of 2x plus 1. And so in g's equation, everywhere we see an x, we're going to write 2x plus 1. So 2x plus 1 squared plus 3. And you can expand and simplify if you like, or you can leave it like that as well. So that is the equation of the composite function g of f. Now the next two questions ask us to find the domain and range. So looking at the equation, this is a quadratic that has been moved left by a half and up 3. So if we look at a graph of that quadratic, that has moved, it's a turning point, happy quadratic, left a half, up 3, looks like this. And we know that the domain of quadratics will be all real numbers. And the range is 3 up to infinity. And so you might be tempted to say that the domain and range for a composite function is all real numbers and 3 to infinity. But we have an issue. And the issue is this restricted domain can do some funny things. So let's look at what's going on using a function machine. So we need to stop and think about the order that we substitute into each function. So looking back at our first example, we substituted x equals 1 into f, we got our answer, and we substituted that answer into g. So you can see that this answer became the x value for g. We're going to make a conveyor belt that sort of symbolizes this. Things go into f, come out of f, go into g, and come out at the end as our final value. So let's make a conveyor belt, and this can be the first piece of machinery that it goes into called F, and a second piece of machinery called G. We have things going in, things coming out that then go into the next machine and come out the other end. So in our previous example, x equals 1 came in, the value that came out was 3, 3 went into G, and the value that came out was 12. But let's have a look at what happens if we wanted to work this out for all possible x and y values, because that will help us work out the domain and range. We've only worked it out for x equals 1, so let's do it for all values possible. Now, before we do that, it's really helpful if you sketch some graphs of your little machines to clearly see ranges and domains quite quickly. So this is 2x plus 1, so it's a linear equation that's been moved up 1 with a gradient of 2. But we have this restricted domain, so it's not the whole line, we need a line segment. So we're going to take a line segment starting at x equals -1, and we have a square bracket, so I will need a closed circle, and the corresponding y value at -1 will be 2 times -1 plus 1, so -1. And at the other end, at x equals 2, we'll have an open circle because it's a round bracket, and the y value will be 2 times 2 plus 1, 5. So the line segment we need is just this piece here. Okay. The second graph is a parabola. It's a positive parabola and it's been moved up 3. And we have no restrictions, so we draw the whole parabola. Let's work out the domain and range for both of our graphs. The domain here is -1 to 2, and the range is -1 up to 5. The domain here was all real numbers, and the range is 3 up to infinity. Okay, let's send in this information onto our conveyor belt. So, numbers that can be sent into F is our domain. So, all numbers between -1 and 2. They are the numbers that are allowed to be substituted into our equation, and the values that come out, or the y values, or the range, was -1 to 5. And this is where the issue lies. Previously, we thought that because our equation is quadratic, that our domain would just be all real numbers. But this assumes that we're allowed to send in all possible x values. What happens here is that our machine we've set up has restricted what can be plugged into G. So we have a restriction coming in, -1 to 5. So we need to go back and redraw this graph and work out what part of the graph can I actually use. So at x equals -1, we are including -1, so I need a closed circle. And my y value would be -1 squared, which is +1, plus 3. So we're at a height of 4. At the other end, at 5, we have a round bracket, so open circle. And the corresponding y value is 5 squared plus 3 is 28. So originally, our range is 3 to infinity, but because we have a restriction happening on our machine, what now comes out the other end is the lowest value being 3 up to 28. Okay, So here's our function machine. We can send in these x values into f. These are the corresponding y values that come out, which then become the x values that go into g, which produce these corresponding y values. So the domain, our domain are the values at the start, the values that are at the very, very start of our function machine. Our range is what comes out at the very end.